Okay. All right, cool. So it says a table of measured data was created by a student during an experiment in which we're looking at amplitude. So the maximum angle of oscillation after 50 oscillations was measured for different masses of the bob hanging on the pendulum. Okay. Measured amplitude. So we're looking at the amplitude after 50 oscillations, right? Okay, so amplitude after 50 oscillations. Okay, good. Sorry, I just needed to visualize that in my head for a second, what's actually going on. The first thing I would do is just copy this data set, the raw data, into your Excel. So just go ahead and copy that into your Excel. And then what you can do is, what you need to do is you need to copy the independent variable. And then you're gonna find the average here. Okay, so you're gonna turn this into average. Because remember, that's what we're doing, right? When we're doing process data table,
Yeah.
we need to have the average, then we need to have the uncertainty, right?
Yeah.
And then that should have auto. There we go. It's just lagging a little. And then here we'll have percentage uncertainty. I'll just write. That's what I'll write. Percentage uncertainty here. Okay. And actually, I'm going to. Actually, this is fine. The way this is written is fine. Now average here is just going to be, for the formula, you're going to just write equals average of all these numbers here, right? And then if we have autofill, it should technically work. Yes. So you can just use autofill to fill in the rest. I just want to make sure we have the right number of sig figs. So this one is actually 23.0, right? So Excel sometimes it's an exact like 23.0, it rounds it and it doesn't show the zero. So let's go ahead and tell Excel to show that zero.
Okay, good. How did you do autofill again?
Oh, so so once you select the cell, there's a little plus sign if you hover over that bottom right corner, and then you drag it down.
Okay, there we go.
Okay.
Did you get 16.8? Okay, all right, perfect.
And then this should also be 16.0, so we're gonna just hit that, and then, oh, that's too many zeros. There we go. So we just wanna make sure that we have the right number of sig figs on here. And then on the Word document, did it say, so that's actually 0.100, there's 2 zeros there, so we need to make sure to show that. Wait, nope. There we go.
How come it didn't let me add extra zeros?
You have to press the little button up here. Did you do that increase decimal?
Increase decimal?
Because there were more sig figs to these, I think, right?
Okay, I'll increase
I think there were, the precision is up to the thousandths place, right?
Yeah.
Okay. So actually, in that case, we're going to need to recopy these onto here, just to reflect the precision. And then we have 21.3. Okay. This has one too many sig figs. This needs to be decreased down. Okay.
Yeah.
So even though we're decreasing it, Excel actually has the raw value stored for this. Okay. So that's why when you might work out the uncertainties and everything by hand, it might be a different value, but Excel is doing everything precisely and then rounding only the final answer. Okay. Now uncertainty is equal to the range divided by 2, right? So we're going to take the max value of whatever's in this range minus the min value of whatever's in this range, and then divide that by 2.
Oh, divided by
2. So that's your uncertainty. Okay. And uncertainty should ideally be to 1 sig fig, so I always do it to 1 sig fig because that's the norm, I guess you could say. And then just use autofill. Wait, I don't think that worked, did it? Actually, it did work. Yeah, it did work. So it turns out that the uncertainty is actually just 1 for each of them.
I got 5 for each of them.
For which one?
For each of them. You said it was max minus minimum, right? So 21.3 minus 11.4.
And then divide by 2. Did you do the divide by 2?
21.3 minus.
See, here's the thing. I never do I don't do the numbers, like, because here's the thing. You might mess up. If you just let Excel take care of it using the formulas, then you don't have to worry about whether you messed up the calculations or not.
Yeah, but I just put it in the calculator. 21.3 minus 11.4 is 9.9. Divided by 2 is 4.95. That's equal to 5. Rounds up.
That's a good point. So which one? So 21.3, or sorry, 23 minus the answer. So it would be 23, right?
Oh, I was doing the averages. Okay, my fault.
23 minus 20.2, and then if you take that divided by 2, you'll get 1.4, which rounds to 1. Yeah. So these are I think these are right. And then percentage uncertainty is equal to this uncertainty divided by the average, I believe, right? Correct me if I'm wrong.
Yes.
Okay. So once you do that, you'll get that number. All you got to do is just hit percentage, and it turns it into a percentage. Let me make sure it did that properly. Yes, it did do that properly. So then just...
Can you do that again?
Yes. So equals uncertainty over average. Hit enter. Then click on that, and then format it as a percentage.
Okay, so...
And then use autofill to fill in the rest.
This divided by this. 0.469. Wait, what?
No. Use your uncertainty. So equals K3 divided by J3.
K3 divided by J3, yeah.
And then just hit enter and then turn that into a percent.
Yeah, it's giving me 0.0469.
0.0469. For which one? The first one?
Yeah, for the first one.
Well, here's the thing. If you just do the one reason, I'm not sure if this is the reason, but if you just take your calculator and do 1 divided by 21.3, that's 0.46. Yes. Here's the issue. This is one of those examples. Yes. This is one of those examples because the real value of the uncertainty is at 1. The real value of the uncertainty is 1.4. Remember, it's more like, so what Excel does is it takes the precise values, then divides them, and then finally rounds them. What we just did to get the 0.0469 was take straight up 1 divided by straight up 21.3, and that'll get you to the 0.0469. But that's technically that's a little bit inaccurate, so I don't do that. I always try and round at the final stage wherever possible. Okay. All right. Good. So now,
well, I'm gonna be honest. Like, you're explaining, but it keeps giving me 5%. I'm very confused.
I think it's because your formulas aren't set up properly here.
Do
you have average of B3 to F3 over here?
Average of B3, I have 21.3, 18.8, 16.8, 14.3, and 11.4.
But did you manually type those in, or did you enter the formula?
I entered the formula for the first.
Okay, good. And then the uncertainties, did you put max of B3 to F3 minus min of B3 to F3 over 2?
No, I don't think so.
That's probably where. So once you fix that, your uncertainties will automatically adjust. And
okay. So how did I equals?
You see the formula bar? Max of B3 to F3 minus min of B3 to F3 divided by 2.
Formula. I'm on the formula bar. I can't find that. Is insert function?
No. It's just the formula bar is just this thing up here.
Oh, so I just typed that in. Okay.
Yeah.
Max parentheses B3
to F3.
Let me full screen that. Max B3 F3.
And this looks like the data is pretty linear. It doesn't look like there's anything weird going on. Actually, there may be. I don't know. We'll see.
To F3 divided by 2. Okay, now it gave my uncertainty as 12.9.
12.9. Hold on. Do you want to share your screen?
Yeah, I'll share my screen.
Let's try that. Okay. Let's see where you're getting that.
It says host disabled participants.
Oh, let me fix that. There you go. You should be able to do it now.
Okay. Okay, so can you see it?
It's loading. Yes. Okay. Let me
Okay.
zoom in a little bit. All right.
So I have this is did I set
Oh,
this?
okay. You have to put parentheses around max minus min. Like yeah.
Oh, okay.
Because otherwise what it's doing is it's doing order of operations. It's doing min divided by 2, and then it's doing max minus that.
Okay, let's run them.
Okay.
That looks
You get 1.4, perfect. And then you need to round that to 1 decimal place.
Oh, okay. What's
hit
happening?
Control Z. Just hit Control Z. Just hit Enter. Hit Enter. And then hit Control Z. There you go.
Okay.
Now up where it says decimal or like increase decimal. Hold on. Yes. So decrease it. Yes, to 1. Perfect. And then make sure the formula is carried through. And
There we go. Okay.
There we go. Perfect. Okay,
All
good.
right. Here, I'll stop my share.
Good. All right. So now what you want to do, the next step in the process, let me just make sure. So that's your process data table. And ideally what you would want to do, I'm not going to put it in the table here because there's no need to do it, but you would write measurement, and you would write reported measurement as 21.3 plus minus 1, 18.8 plus minus 1, and so on and so forth, right? But I'm not going to put it here because there's no point. Okay, let me go back to the word here. Create a graph. Okay, when you're creating graphs with data points like these, so what you'd want to do is you'd want to select just these values right here, and then go to Insert.
Okay.
Scatter plot right here. You're gonna click on scatter plot, and you'll just click on the first one, scatter plot. Okay. All right. Once you have the scatter plot, you're gonna need to format this a couple ways. The first thing is you're gonna click on this plus sign right here. Yep. You're gonna say axes titles.
Okay.
We want axes titles. We don't need data. We need error bars. Okay. So let's figure out the error bars first. So you're gonna click on error bars, and then you're gonna click on more options. Okay.
Should I turn on the error bars before I click more options?
Yes. Yeah. Click on error bars and then click on more options.
Mm-hmm.
For horizontal, so now what you're gonna do is just click on these horizontal bars right here.
Okay.
So our horizontal uncertainty was plus minus 0.001, right?
Yeah.
So now I'm gonna go to this. Once you click on the horizontal error bars, this should pop up. Did this pop up right here?
That side taskbar, yeah.
Yes. So like if you, that side taskbar, make sure you go to this graph looking icon that gives you everything that has to do with the math aspect of this, these error bars. You're gonna, both direction is both. You do want to cap, and then it's a fixed value, right? Because the value is fixed at 0.001. So let's go ahead and just enter that in.
Okay. 0.001.
0.001. Okay, and then hit enter, and there you go. So now it's adjusted. And honestly, it's so small you can't even see it, but it's there, right?
Yeah.
Okay. Now, same thing, but for the vertical ones, it's variable. The uncertainty is variable. It's not the same. Well, in our case, it is because they rounded to the same thing, but technically they're not the same. So what you're going to do is similarly, you're going to go to graph, and then you're going to click on custom.
Okay.
And then specify value. And for the error range, like for the positive error value, you're just going to select this range. And for the negative error value, oh, why isn't this working? That did not work. Okay, let me try that one more time. Specify value, okay. And then for the positive error value, it's that. And then for the negative error value, you might have to hit enter and then do it again. The negative error value is also that.
Should I delete the 1? There's already a 1 there. Should I delete that?
Where did it say 1? Oh, yeah. Delete that and then
1 plus sheet.
Yeah. Okay. Delete that and then select the sheet.
Okay. And then for negative, what do I put for negative?
For the same thing, because remember, it's
because
sometimes plus I don't know when that would happen, but your positive uncertainty might be different from your negative. But as you can see, even though in our graph here they're all 1, and when you would do it by hand, you would actually do plus minus 1. Here you can see though that some of them have greater uncertainties than others, right? Because like remember this one was like 1.4, whereas this one might be closer to 1. Yeah. So Excel just does everything more precisely and it rounds at the last step. So when you're doing this by hand, you would need to make sure that you make it consistent with whatever you've done here. Or if you round in the final step, then just specify that. So just be clear about it, okay? Now we can go ahead and write our chart title. This is a graph of amplitude after 50 oscillations versus mass of Bob. Okay, and then axis title here is mass of Bob in terms of M, and we're representing mass with the letter M. And essentially the units is kilograms, so it's mass divided by kilograms. Because, does that make sense if I wrote mass over kilograms?
Yeah, so do we have to include the uncertainties in the chart title? So do I have to
Not in the titles, because the error bars would do that for you.
Okay.
Yes. And then the axis title here would be amplitude after 50 oscillations. And you might choose to give that a variable letter. Let's call it capital A. Okay? We're going to call it capital A. And the reason we're doing this is that way when we write our equations later, we have a real world like meaning for those equations. And it's A per degree. You're going to have to go to, if you wanted to insert that, you would have to go to insert symbol and then look for the degree sign in here, which I hate sifting through. I wish they had a search feature on.
I think what my brother showed me last time is just to go online, search up like
the alt code.
Yeah.
Or you can copy paste. That works too. Yeah. So there you go. So that's the degree sign. Done. Good. Okay. And degree isn't really a unit, but we're treating, in this case, we need to specify that it's in degrees or rather than radians. Because if you don't put a unit there, then it's it's assumed that it's radians. Okay. So now that we have our main graph, we need to create our line of best fit, right? So you're gonna click on plus, go on trend line, click trend line. All right. If you go to more options, you can. I'd like to make my trend line the best line. I like to make it solid, so I make it a solid line, and then dash type, I make it solid. That way, it goes straight through, and you can see that.
Solid line and then dash type solid.
Yes.
Okay.
And then I'd like to make this one green. I like to color code it just for my own sake. So I remember, okay, so this is my line of best fit. And what Excel does, and I love Excel for this, if you go to the graph thing over here, say for example, this was an exponentially looking graph rather than linear, you could just click exponential and it would work. In this case, it's obviously, it's linear fits better, right?
Format trend line, graph line. Yeah, linear would be better, yeah.
So, but here, it actually gives you, so what I do is, if you go down here, it says display equation on chart and display the R squared value.
Yeah.
If you do those both, that gives you your equation right there, actually. And that actually, like right off the bat, you know what your slope is. Your slope is negative 121.8, and your y-intercept is 23.82. The R squared value is just a measure of how closely the values fit the trend, predicted trend. Let me confirm that actually, real quick. Because the Pearson R coefficient actually tells you how well they are correlated, like how well the data is correlated, but I'm not sure what R squared is.
What would the U? Because it
R
says
squared?
it said calculate the slope of the line of best fit, but it says.
Okay, we'll get there. We'll get there. R squared is the coefficient of determination, and it represents the proportion of the variance for a dependent variable that explained. Okay. So it says, whereas correlation explains the strength of the relationship, R squared explains to what extent the variance of one variable explains the variance of another. Okay, so that means almost 100% of the data set of the independent variables can explain the dependent variables. So this is very good that it's almost 100%. That's like near ideal, right? Now, when we get to the unit of the slope, okay? The unit, so in this case, M, actually, let me write like this. Let's do this. I'll write slope here. I'll write y-intercept here. And then here, I'm going to write best value. Then here, I'm going to write it for the max line. Actually, I'll leave a space there. And I'll show you why later. And then here, I'm going to call it for the min line. And we know for the best line, it's negative 121.8. And then y-intercept is 23.82. Now, whenever you're doing units, okay? the unit of the slope is always y over x, right? Because what is the slope formula? It's y2 minus y1 over x2 minus x1. So ultimately, you're going to get y over x as the units. So in this case, the units would be degrees per kilograms.
Okay.
Okay. So that's so the slope is negative 121.8 degrees per kilograms. If you want to be precise about sig figs, okay, we'll get there later. So this is the raw calculated value, right? Now, if you wanted to calculate the slope by hand, then the best way to do it is just to take this value minus this value divided by this value minus this value. It's just like calculating the slope.
My cell is glitching. I have no idea what's happening.
Sorry,
Okay.
Okay.
I think I fixed it. So
I said, so if you want to manually calculate slope, the way I do it is I just take the slope formula y2 minus y1 over x2 minus x1. And then I just plug in the first and the last value. So I do 11.4 minus 21.3 divided by 0.1 minus 0.02. And I'm just going to put this in my calculator here. 11.4 minus 21.3 divided by 0.1 minus 0.02. And that gets you negative 123.75. Which isn't far off from what we got, so it's reasonable. So if you do it by hand, it's reasonable. And then y-intercept. The way I do y-intercept is actually by using the point slope form. Do you remember point slope form? It's y minus y1.
Yeah, my y minus y1 over x minus x1.
So y minus y1 times is equal to m times x minus x1.
Oh, I remember this. Yeah.
Okay. So now you can just plug in. Let's just choose the first one right here. This data point. Y minus 21.3 is equal to our slope, which is negative 123.75. So as you can see, when you're doing it by hand, eventually your data is going to get further away from the exact value, but that's fine because you're doing it by hand and you're showing your work. That's completely fine. So you're going to expect your answer to be a little bit different from what's here. Times x minus 0.02. Now, if we can convert this to slope-intercept form, then we found our intercept, right? So the way we're going to do that is by isolating y. So that means y is equal to negative 123. I'm just going to write m because the slope here isn't really important. Mx
plus 21.3.
Well, plus 21.3 plus, we have to distribute this, right? Plus the 123.75 times 0.02. So let me just do that in my calculator real quick. 123.75 times 0.02. That gets me 2.475. And then if I add these two together, then that means the y-intercept is that plus 21.3. And it's 23.775. That's what I got. And if you wanted to round to the proper number of sig figs, you would probably say it's 23.8. Okay. And that's actually what we got with our model here, right? So it's a pretty good model. Good. Okay. Can I clear the screen now?
Yeah.
Okay. So I'm not going to go through the manual process again because for the max and min line, once you figure out the 2 points, you can just use the same process of doing the slope formula and then the slope intercept form. If you use the point slope form and convert that to slope intercept, you can find the y-intercept. So I'm not going to show that again, just because you can do that.
Yeah.
Then next is the max line, right? So max line, you have to, it's a little bit more conceptual and you really got to think about this, okay? So we're going to call this right here, we're going to call this max line. I just merged those two cells and I called it max line. And then I'm going to merge these two cells and call it min line. I'm going to plot my x value and my y value. Same here, I'm going to plot x value and y value. Now for the max and min line, remember, we only worry about the first and the last points, right? So this data right here, this stuff all in here doesn't matter. So I can actually just black it out. That way I'm not worried about that, okay?
Yeah.
So now what you have to kind of visualize this, okay? So the max line is going to look like, so remember we have our boxes, right?
Yeah.
So the first box would look something like this, okay? And I'll just exaggerate the box a little bit just so we can better visualize it. And then the second box is going to look like this, right?
Yeah.
Okay. Now the max line, let me change the color so you can see. The max line is going to be from this corner to this corner, right?
Yeah.
Because anything else would produce a slope less than that. So the max line is going to be from there to there. So let me just draw that line using my annotate feature first. So I'm just going to visualize it first, and then I'll draw the actual, figure out the actual numbers later. So that's the max line. Now similarly, min line is going to be from, let's use blue for min line. Min line is going to be here. Actually, did I do this wrong? No, I did. I think I did this right. Min line is going to be from here to here, I believe, right?
Yeah.
That's the line that would produce the smallest slope, I believe. So min line then would be, if I were to draw that line, it would look like this, right? Okay. All right, so based on this, for the max line, okay. So max line, think the red line. For 0.20, x, it's whatever the x value is plus the uncertainty, right? The x value.
Yeah.
And if you get confused, just let me know, because this is where it gets a little bit tricky. So you take your average plus the uncertainty.
22.3.
Sorry, not your average. I'm so sorry. This is the x value we're dealing with. So we're doing the x value plus the uncertainty. Our uncertainty for x is always going to be 0.001, right? So that's the uncertainty. So that's the x value of the max line for the first point. The y value is going to be equal to what?
Hold on. 0.040 plus 1 is...
No.
Wait.
The y value for the first point.
Oh, 21.3. Do you add 1?
Add 1, right? You would add the uncertainty here. And actually, you can see that it's not actually purely 22.3. It's 22.7 because, once again, Excel is using that exact value, remember?
Right. Yeah.
So max line, as you can see, it's x plus delta x and y plus delta y. Now, what about for max line, this minimum point? It'll be x minus and y minus the uncertainty, right? So we can just do that again. So it'll be this minus the uncertainty of 0.001, and then the y value would be this minus the uncertainty, which is here, and that gets you your max line coordinates. Okay?
Yeah.
Okay, now we're going to do the same thing for min line using the same logic. It'll be the min line would be massive Bob, or right? But this time it's minus, right?
Yeah.
So I3 minus 0.001. And then y value is also whatever the average is minus the uncertainty. So we're going to say average minus uncertainty. Okay?
Yeah.
And then x value here for the min point here is x value plus uncertainty. This plus the uncertainty of 0.001. And then min line here is equal to the y value minus the uncertainty, right? So it'll be this minus 1. Hold on, never mind. It's not minus, it's plus, right?
Yeah.
So that should be plus. Okay. Do these data points look right? They look pretty correct. Okay.
Yes,
so now what I'm gonna do is I'm just gonna erase my annotations. So now what we're gonna do is actually plot them. And once we plot them, we can actually figure out if we did this properly. So once again, what I'm gonna do is I'm gonna select this data point. Actually, I'm gonna select these two and these two. Oh, that's not what I meant to do. Those two. Hold on. That one. Actually, hold on. I'm so sorry. I forgot how to do that for a second. So what you're gonna do let me just move the equation out of the way so we have room to actually show it. What you're going to do is you're going to click on this little filter button right here. Okay? Select data, and you're going to hit add. Okay? You're going to create an add. The series name is called maxline. The x values of the series are this one, and then press Control, and then select this one. That lets you select non-consecutive cells. And then for the y values, you're going to have this one, and then hit Control, and then select this one.
Okay.
And there you go. Do you see how it plotted those points?
Yeah.
Good. So now, similarly, we're going to do the same thing, but for minline. Add. Series name is going to be now be minline. The x values are going to be this, control this, and then the y values are going to be this, control this, right? Hit enter, and there you go. So I'm going to color code this a little bit differently. I'm going to make my min line be colored blue. I feel like blue works well as a min line color. Just visually thinking, that just helps me. And I'm going to choose a light blue, otherwise it doesn't show up. Hold on. Yeah, there we go. Make that blue. Okay. And then for the max line, I'm going to make it red.
Yeah.
Okay. Good. So similarly, now to find the trend lines, we're going to do the exact same thing. We're going to click on the plus sign, and then we're going to click on trend line. And the trend line, actually, for these, I keep dashed, but I make sure to go ahead and change the color. So the color I go ahead and change from gray or whatever it is to, in this case, it'll be blue, right? Good. And then our max line would be, oh, I forgot to show equation. Display equation on chart, display r squared value on chart, and there you go. That actually, in this case, you don't need an r squared value, because when there's only 2 points, there's only one line that can cross the 2 points. So of course your r squared is going to be 1, right?
Yeah.
You don't need to know that, but does that make sense why it would be 1?
Yeah.
So you don't need to, you just need the equation. And then I'll place that below here so that you know that's for the min line. And then for the max line, we're going to select that series. And similarly, we're gonna go on the plus sign, click on trend line, and then go to more options, and then once again display equation on chart, and there you go. Okay, so now we know that our max line slope is -155, right?
Yeah.
Our min line slope is -95, right?
Yeah.
The y-intercept of this one is 25.975, right?
Yep.
And then the minimum slope, or sorry, minimum y-intercept is 21.725, right?
Yeah.
Okay. So now we're going to find the uncertainty in each. So to find the uncertainty in the slope, we're going to do the maximum minus the minimum over 2. However, we have to be careful here, because even though this is the max line slope, this one's bigger than this one. So we have to do the range max minus min
Divided by 2.
divided by 2.
Okay.
So the uncertainty here is 30. Now, I'm not sure, actually. Let's think about it. If I did this minus this divided by 2, you get -30. So no biggie, right? Because at the end of the day, what it's doing is it's finding the magnitude and then dividing by 2, I believe, is what it's doing.
Plus
right?
or minus 30.
So it's plus or minus. It doesn't really matter. And then, let me make sure. Okay. And then here, it'll be this one minus this one. Oh, I don't know what I did there. Okay. And 12 minus P12, that thing, divided by 2, okay?
21. Or 2.1.
And honestly, your y-intercept should only be expressed. These have too many sig figs. You see how your averages only have 3 sig figs?
Yeah.
And your uncertainty actually only goes to 1. So honestly, your averages should have been counted down. So honestly, your averages should have been gone down to 21 instead of 21 point. So in this case, this might be a case where I keep two sig figs in my uncertainty. Do you understand why I'm doing that?
Yeah.
Otherwise, it just looks weird, right?
Yeah.
To make it 21, 20, or whatever. So this might be a case where I end up using 2 sig figs. Our y-intercepts need to be rounded to the 10th place. So let's go ahead and do that. And once again, remember, this final uncertainty that's being calculated is not the 22 minus 26. It's actually, or 21.7 minus 26. It's actually taking the raw values of it and then taking the rounding finally. So uncertainty, once again, in this case would just, oh, what am I doing? There we go. It would be 2.1 in this case, the uncertainty. And then in the slope, I think the uncertainty is rounded already to 1 sig fig, so that's fine. Yeah. Okay. And the best slope needs to be rounded, I think. The best slope is too far. The best slope needs to be rounded to -1.
Okay.
Okay. So now that we have all our things, we can write an equation. Y. Actually, does it let you insert equation in Excel? It does. Okay. So if we is LaTeX in here? LaTeX is a formatting tool that we use. No, it's not. That's fine. It'll auto format anyways. So our equation in this case is y equals mx plus b, right?
Yep.
So what is m in this case?
For the best line?
Huh?
For the line of best fit?
Yes.
Negative.
Yeah, sure. For the line of best fit.
-122.
Y equals -122x plus what? 23.
Plus 23.8.
Okay, so that's your mx plus b, basic. Now, say I wanted to represent this in terms of mass and amplitude using my variables m and a. All I got to do is just replace it now. So now I'm going to write a, the amplitude, is equal to, -122 m plus 23.8. Do you see what I did there?
Yeah.
Okay. So that's for your best fit line. Okay. Maybe I might want to fill this white so that we can see it. Yes. Okay. Good. So this is for your best line. For your max line, you can do the same thing. Your max line, it'll be -155x plus 26.0, right?
Mm-hmm.
And this is all, if you like, it's all directly shown in Excel. But I'm just saying, like, this is for when you report your final answer. This is a equals -155m plus 26.0, right?
Yep. This is for the max line?
Yes. And then for the min line, it'll be -95x plus 21.7, right?
Mm-hmm. So you don't have to express the function uncertainty or the line.
We'll get there. Yeah. Okay. And then this is 21.7. Okay. Now that we've done all this, now that we have an uncertainty, now we're going to write our final line. Essentially, what it'll be is y is equal to m plus minus delta m. I wish delta like automatically went in there. If not, then I'll have to, oh, that's not what I meant. I'll have to manually enter in delta. Greek letters, alpha, beta. Okay, we need the capital delta. Okay, there we go. Over delta m, and then b plus minus delta b, right? That's essentially what we're saying. That means y equals -122 plus minus 30 x plus 23.8 plus minus 2.1. And then that means the amplitude is equal to the same thing. I can just copy and paste this.
So when she says on the lab reports, so like for example on the major quiz it says calculate the slope stated in words.
Well, yeah, we'll do that too.
Okay.
23.8 plus minus the 2.1. Okay, all right. So math-wise, we are done. This is all the math you got to do, right? This is all the math you have to do.
Yes.
So this is fully processed data. I don't think there's anything else we can do with this. Now, discuss the results. What's the dependence here? I think that's pretty obvious. What type of correlation is this?
Wait, what do you mean? What do you mean?
This is called a linear correlation, right?
Yeah.
So it's linearly correlated. That's the dependence that you discovered. So if you want to be precise, what you're going to say is amplitude has, or here I can say the mass of Bob and the amplitude after 50 oscillations is linearly correlated. The correlation is negative. You can specify that as well, because there's a negative slope, right? Okay. And this is what you would be, and I'm not going to write out the full thing for all of it because it'll take space, and I don't have the space on my screen for that. But that's your results. State in words the slope and uncertainty of the graph and its physical meaning. Okay. The slope is negative 122 plus minus, and obviously here I can't draw out the plus minus sign because it's using zoom annotate rather than the equation feature. So negative 122 plus minus 30. And what's the unit of the slope? What did I say slope was?
Degrees per kilogram.
Yep, degrees per kilogram. The slope is negative 122 plus minus 30 degrees per kilogram. Practical meaning is there's a very nice formula that you use. This means that that the amplitude decreases. Here you can write it this way as well. The rate of change. See, I don't want to say rate of change because that implies derivatives and instantaneous. Because this is what we do in calculus. In this case, I guess you could say that this means that the amplitude here changes at a rate of negative 122 plus minus 30 degrees
per kilogram.
Per kilogram.
Okay.
Or if you want to be a little bit more specific, for every 1 kilogram that you increase, that's another way of putting it. For every 1 kilogram that you increase, your amplitude changes negative 122 plus minus 30.
Okay.
Okay. You're going to do the same thing with the y-intercept, right? The y-intercept, let's do that real quick. The y-intercept is 23.8 plus minus 2.1, right? And what would the unit of the y-intercept be?
It's not kilograms per.
Okay, remember, the y-intercept is just a point on the y-axis. And what does y represent? Degrees,
amplitude,
right?
so just capital A. Oh, degrees, yeah.
Yeah, so it's 23.8 plus minus 2.1 degrees. Y-intercept is whatever the value is when x is equal to 0.
Oh, because the slope is the change in
change in y over x. Yeah. As soon as you think of slope as y over x, calculus makes a lot more sense, and that's something that I've been trying to tell some of my classmates in calculus, and it really helps, I think, to visualize slope that way. Okay, the y-intercept is that, and then this means that with a Bob means that for Bob, I don't know if Bob is a capital B or I don't know. Like, is Bob a figure? Is that the name of the thing? Is that what they're calling a Bob? Or
I
what is a Bob?
think she said Bob like
Oh, it's something.
Bob's,
Oh,
yeah.
okay, got it. Okay, I didn't know that was called a Bob. Anyways, we'll just keep it capital B because for consistency. This means that for Bob, let's just pretend like the Bob is named Bob. Okay, this means that for Bob, the Bob with a mass of 0 kilograms. This means that for a Bob with a mass of 0 kilograms, the amplitude after 50 oscillations is 23.8 plus minus 2.1 degrees. Okay, does that make sense how I got that?
Yeah.
Okay, so remember, because y intercept is...
Oh, when x, so basically it's saying when x equals 0, y equals 23.8 plus or minus 21.
It's literally, if you think in terms of x and y, and then convert that into your real world scenario. Okay. Okay, now dealing with the random and systematic errors. The random error it doesn't seem like there's a very okay, systematic error doesn't seem very high, does it?
No, not really.
So you would say it's very difficult to tell if there is a systematic error, but in this case, it seems like it's pretty consistent, right? Because that would make sense. It would just make logical sense. So there does not appear to be any systematic errors. Grammatically, that should be there do not appear to be any systematic errors. Now, random error. Let's calculate the percentage uncertainty so we can quantitatively tell them if we have high random error. So random error in this case, random error is going to be looking at percentage uncertainty. And percentage uncertainty is equal to our uncertainty divided by our best. And then same thing here. This value divided by our best. And this should be a positive. So I'm just going to take yes, okay. I'm just going to take the absolute value of this, make it a positive, and then I'm going to make this a percentage. I'll make this a percentage. The issue is here. The issue is with this on. So we would specify then. There does not appear to be a random error in the y-intercept. However, there is a huge random error in the slope, right?
Yeah.
So you would elaborate on that there and talk about what may have caused that random error and what. And that's pretty much it. If you do everything here, some of you, like, obviously it'll take more time when you do it on paper. And I was trying to do it on Excel and do it on my my paper at the same time, so I could check back and forth. But that's pretty much everything you would need for processed data, lab report, whatever.
Mm-hmm.
Okay.
Thanks.
How did we get to 55 minutes?
Is it actually?
Yeah, I don't know. Usually Zoom meetings end at.
Oh, wow.